Hello everyone, here we'll be discussing 6.3, which is volumes by cylindrical shells. This is actually kind of a continuation of our discussion from 6.2, which was volumes by rotation. So we're still going to be looking at the same kinds of problems, but the technique is a little more sophisticated and it's a little more specific actually. So let's see what happens. But before we get there actually, let's recall what we learned from 6.2. And this problem will kind of give us a little bit of a run for our money. It's still doable, but it's a little more complicated. So let's see, it says find the volume of the solid generated by rotating the region bounded by y equals x minus x squared and the x-axis about the y-axis actually. So just to get an idea of what's going on, if you actually factor this, notice it factors as x times 1 minus x. So its zeros are when each of those are zeros, which is at x equals 0 and at x equals 1. And furthermore to downward parabola because the number in front of x squared is negative. So it will look something like this, actually. Now notice the region bounded by this curve and the x-axis, remember obviously this is the x-axis, this being the y-axis, would be this shaded region right here. So the region that we're rotating about the y-axis is defined. We understand what that is. It's understood. So now we don't actually need these arrows. So really just this piece right here. And if we rotate this about the y-axis, the shape we're going to get, I'll do my best to try to draw this in a perspective type of way. It reminds me kind of like a jello cake kind of a deal, or I don't know if that's what you'd call it. Just be like upside down jello thing. So something like this, but all the way around, which is really hard to draw. I'm trying my best to draw it, but I don't know if I'm quite doing it justice or not. But that's kind of the shape I imagine getting. Because just imagine this is swung around, you get this kind of bun looking thing. I don't know how else to describe it. But yeah, so let's see, how do we find the volume of this shape? And notice there's no hole, so this is actually not a, well, it's not really a washer's problem, but it actually kind of is, because if you take a look at, because remember we're rotating about the y-axis. So if you take a look at a particular, and it's a little kind of hard to follow, but if you take a look at a particular cross-sectional area, let's just say something like this. So imagine this is again rotated about like that. So these things are being spun around at a particular point, let's say something like this. So this would be the hole at that point, and this would be the, I guess, interior at that point. So at the cross-sectional part, they actually are washers. Even though it's not completely hollow of a shape, part of it kind of is because it has that little divot in the middle. Okay, so that part I think kind of makes sense, but it's still really weird because we have to first off view this as well, it's a y-axis problem, so we kind of have to view this sideways a little bit. And I'm going to actually do us a favor. I'm going to draw this again, but sideways. So this is our y-axis, this is our x-axis, and then we actually have this shape kind of like this. Now the problem here, of course, is that this shape like this is not actually a function of y because it fails the vertical line test. And this is actually a scenario we haven't seen so far from 6.2, and this is where the method of cylindrical shells will come into play and help a lot. Because notice really what we have to do is we would have to find the cutoff point where this thing is intersected by two separate functions and split it up like that, which is actually doable, and I kind of want to show you, but I feel like it'll take a little bit of time. So basically, since this graph, y equals x minus x squared, is symmetric about the line x equals 1/2, which is just basically the axis of symmetry, you can say, then we can actually split this into two. And I know that sounds kind of weird, but it has to do basically with completing the square, and it's a little complicated, but I feel we deserve kind of to see it. So the first thing I'm going to do is I'm going to actually try my best to complete the square and write this as negative x squared plus x plus something minus something. So the only thing is we need to pull this negative out. When we pull the negative out, this symbol flips like that. Now what number must we add in order to complete the square? It must be half of the middle one squared. So half of this is, well, this is 1. Half of 1 is 1/2. Squared is 1/4. So now it sounds kind of complicated, but all I'm doing really is completing the square. And notice actually what we would need is positive 1/4 here, because after distributing the negative, you would get negative 1/4 and it would cancel out. And furthermore, this would actually factor as x minus 1/2 quantity squared, and that's the whole purpose of adding and subtracting that 1/2 in kind of this funny way. So now we can actually solve for x in terms of y, but we'll get two scenarios, a plus or minus, because we square root. So let me just kind of border this off to show that. So if we subtract 1/4 to the other side, and we get, well, negative this, but if we negate the whole thing, so let me actually do that. So again, I'm subtracting 1/4 to the other side, but then dividing by the negative in front of here gives me this all to the second power. And then if we square root both sides, we get this outside of the power equals plus or minus the square root of 1/4 minus y. Perfect. Then add 1/2 to the other side, and finally we get our solutions. Well, not solutions, but we get our functions anyways. Now the funny thing about this is that there are two functions, of course. So one will be the upper half of this, and one will be the lower half. And in fact, it's not difficult to tell which one's which. The one with the positive is the one that faces up. Let me just kind of see what's going on here to see if that makes sense. Yeah, so the positive one is the one that's facing up, and the one that's negative is the one that's facing down. So you kind of have to extend these to see that though. So if you extend this curve, it would extend like this. In fact, I guess we can plug in values to see which one's which. So for example, if we plug in y to be 0, it's either going to be 0 or 1. So let's see, if we plug in y equals 0, that cancels and we get 1/2 plus or minus the square root of 1/4, which is 1/2 plus or minus 1/2, which is either 1 or 0. But if it's plus, it's positive 1, and if it's minus, then it's 0. So this one up here is going to be x equals 1/2 plus the square root of 1/4 minus y indeed, and this one is going to be x equals 1/2 minus the square root of 1/4 minus y. Awesome. So again, a little complicated, but it's still kind of doable. Now, why do we exactly need this? Is because, again, this is not actually a function. We need a function. So we have these two functions now, so we can determine the inner and outer radii. If we pick any value in between these on the y-axis, now notice that this guy right here is plugging 1/2 into this to get our y value. When you plug in 1/2, it's easier to see when it's factored. 1/2 times 1 minus 1/2 is 1/2 times 1/2, which is 1/4. So really our integral will be going from 0 to 1/4 for the volume. We have pi on the outside, remember how that goes. The inner radius, which will be this distance here, which is on the bottom curve, squared. So it's going to be 1/2 minus the square root of 1/4 minus y quantity squared. And then, well, actually it should be outer minus inner squared. So that's fine. Let me just, let me do that actually. So the outer one is the plus one. So let's just make it like that. And then minus the other one squared. So that's 1/2 minus radical 1/4 minus y quantity squared. And again, this is because the volume of a washer scenario rotated about the x-axis is, remember, it's the volume equals pi in between our bounds of the area of the washers, which is the outer radius squared minus the inner radius squared times dx. Where the inner radius and outer radius are our functions, so we have two functions here, top and bottom. The funny thing is, again, there were actually one function, but when you rotate it, it's no longer a function in y, but you can actually split it into two separate ones. That's what makes this complicated, and obviously we're taking a little bit of time here. So this is kind of our setup. I'm going to erase everything and actually show what this entails, so let's do that right now. All right, so all agree so far this is a pretty intimidating looking integral, but after simplifying, I think it should be doable. So if we square this binomial out, we get the first one squared, 2 times their product will just be the radical, actually, plus the last one squared, which breaks from the radical, so that's 1/4 minus y. That's the first guy. Minus the second one, which I'll actually distribute the negative all in one shot, but let's do this first. So we're going to get 1/2 squared, which is 1/4. 2 times their product, which is just going to be negative this radical. That's kind of nice. And then plus the last one squared, which actually breaks the radical, and we just get radical 1/4 minus y, like that. Okay, And like I said, I'm going to distribute this negative, and in fact, we don't even really need these parentheses. We're still in the integral between 0 and 1/4 though, so keep that in mind. Pi on the outside, dy here. So I'm distributing the negative, changing each of their signs as so. Perfect. And does anything actually cancel? Oh, by the way, my mistake. This, there we go. That radical was gone because when you square the radical breaks, like I mentioned. So that means this would have been 1/4 minus y, but then distributing makes this a plus y now. My mistake. Great. So now do we get any cancellation? And we do actually. Everything except for the radicals cancels out. The 1/4, yeah, that's kind of funny, but the 1/4 cancels with this 1/4, and this 1/4 cancels with that 1/4. So you could combine to get 1/2 and negative 1/2, but that's okay. And the y's cancel. And we're left with these two that are actually the same, so we can combine them as 2 times that radical. But 2 is a constant, so let's pull it out of the integral. So now we have 2 pi times the integral from 0 to 1/4 of 1/4 minus y to the 1/2 dy. Now this is a simple u substitution problem, and it's pretty apparent that u is going to be the inside. So if we let u equal 1/4 minus y, then du is just going to be, of course, negative dy, which of course means that dy is equal to negative du. Usually when this happens, by the way, when we change our limits into u limits, instead of smaller to bigger, we get bigger to smaller, and then we can reverse that using an integral property that we kind of haven't seen in a while to get rid of the negative. So let's see what that's all about. So this is equal to 2 pi on the outside, integral between the new limits, which I guess we'll handle right now. I usually like to do it after, but that's okay. So let's see, when you plug in 0, you get 1/4. And when you plug in 1/4, you get 1/4 minus 1/4, which is 0. So we indeed get actually a straight up swap of this, which is nice. dy is replaced with negative du, which we can pull the negative out, so I'll do that if you don't mind. So let me just kind of do this kind of maneuver. And now we have u to the 1/2 du. Because remember that dy is negative du, but we pulled the negative out, so that's fine. And now, like I said, there's an integral property that says if you have the integral of something d whatever, in this case it's du, but let's just say it's dx, from a to b, you can actually swap these limits to be from b to a and make this a negative integral instead. Which makes sense with FTC part 2 especially, because this basically says that we're doing antiderivative of this plugged in with the top minus plugged in with the bottom, but then it's negative, so it actually is the other way around. So we can get rid of the negative by making it positive, like this, and then swap those limits of integration. So I hope that part makes sense. Now as far as the antiderivative goes, that part's super simple. It's going to be u to the 3/2 divided by 3/2, which is 2/3, multiplied by 2 pi. So altogether this is 4 over 3 pi, evaluated between 0 and 1/4. So we got 4 over 3 pi, and then we're actually going to do this evaluation in one shot here. Now of course when you plug in 0, we just get a 0 into this because it's a power of u, a power of the variable. When you plug in 1/4, 1/4 to the 1/2 is the square root of 1/4, which is 1/2 itself. 1/2 to the 3rd is 1/8. So actually all we get really in parentheses here is 1/8. And we get some nice cancellation here. Notice 4 goes into a twice. So really what we end up getting is 1/6 pi, or if you like, pi over 6. So the answer actually ends up being super nice, but this was a pretty crazy problem. This is a very, very challenging problem with the 6.2 techniques. And now the moment you've all been waiting for, finally we'll talk about cylindrical shells, the technique that 6.3 introduces. Alright, so here it is in all its glory, cylindrical shells. So it's a very specific version of cylindrical shells where we only have one function, but anyways, let's read. So it says the volume of the solid generated by rotating the region under the curve f of x, y equals f of x, from x equals a to x equals b, about the y-axis is given by this. So we have v equals 2 pi times the integral from a to b of x times f of x dx. Now, what is this all about? Why is it x times f of x? What happened to our squares? And why is it 2 pi? Well, let me try to explain. So first off, we're rotating this about the y-axis. So we have to have an understanding as far as what the visualization is, and that's that we're flipping this around like this, and spinning around like that. So in reality, we're spinning this whole object around like this, and we kind of get this ring that's bumpy on the top. Kind of like the previous one we got, but the previous one didn't really have any actual hole because it connected to the origin, but that's a special case. So the way we're actually going to find the volume in this case isn't by considering the washers, but instead by considering these cylindrical rings, which are known as cylindrical shells. So the way we do that is we pick a point in between, call it xi, and then another one called xi plus 1. So we know the deal here. We're kind of splitting this A and B interval into subintervals of, with, you guessed it, delta x. So then we're going to approximate this by a rectangle, and then if we swing this shaded rectangle around, what we end up getting is this piece of a cylinder. So I kind of drawn it cut in half. But you kind of see that if you were to do it all the way around, you get something like this. So maybe that does it more justice. But this is half of it, and then if you swung it all the way around, you get the entire thing in its completion, which would look a little more something like this. Which is definitely kind of nice to see, and of course that would be a solid ring here. So now, the way we actually find the volume of such a piece, or such a solid, is we would actually cut it in half and stretch it out into a rectangular prism. So what do I mean by that? Well, imagine we again have this ring, this cylindrical shell, that has a width of delta x. And let's make an incision somewhere, let's call it right here, let's say. And notice this thing on the inside is something like this. Trying to do it justice. So we're making the incision. In fact, let me do the incision part in red so we can see that better. So here's our incision. So we're making this cut here, and we're going to stretch out this ring so it's a straight box, basically. So now if we make that transformation, if you will, we make that stretch, that doesn't affect the volume of the shape. We're not actually stretching anything, we're just reshaping it, but we're not messing with the actual volume. So all the volume stays the same, still accounted for. Now, first off, notice for this prism, there is a width, which we know is delta x, that part's fine. There is a length, which we'll talk about shortly. And then there is a height, which we need. And in fact, the height part is no mystery. The height is literally the height at that particular x value we choose in the subinterval. So it's really just f of that x value. So let's call this f of x sub I. Okay. Or if you want to call it xi star because it's some point in between the subinterval, that's fine. But I'm going to be working with, let's say, the right limit, so that's fine. Or I guess the right, would it be the right one? I guess it'd be the left endpoints, but it doesn't actually matter. We're still going to get a Riemann sum, and we know it'll convert into an integral. In fact, we already know what the answer is here. But let's just kind of see what happens. So now notice, what about this length here? Well, this length has to be the circumference of, well, either the outer or the inner circle, because there's an inner circle and an outer circle. So which one it is actually is a little hard to describe, but since we're setting delta x to 0 anyways, because we want these things to be very, very thin, it actually doesn't matter. So might as well just call it the inner one that corresponds to this value x sub I. So in fact, if this distance from here to this point where, so from the center, in other words, to here, to create a radius, if that distance, of course, is x sub I itself, because we're going from x equals 0 to this x sub I value, if that makes sense, this will end up being the radius of this circle. So the circular base, let's say. So to find the circumference, which is actually just this length around, if you stretch this out, will be exactly 2 pi times the radius, x sub I. Then what do? Then we take the sum of all of these volumes from A to B. So that's the sum of, well, the volume of this is going to be, again, each of these dimensions multiply to each other. So in no particular order, it's 2 pi xi times f of xi delta x. And specifically here, I guess it's going from I equals 0 to n minus 1 because it's a left, the way I've described it here, it's a left limit or a left estimate or left point rectangle estimate, whatever you want to call it. But then anyways, if we take the limit as n goes to infinity, then what happens is this just actually turns into the above thing, the integral between our limits a and b, and then we have 2 pi xi turns to x, f of xi turns to f of x, and delta x turns into dx. Just because this right here is basically our function. In other words, it's the same thing as our integrand, only with x's instead of x sub i's. And we get exactly this, only here I'm pulling 2 pi out, of course. Now, if we have a bottom function, then we can actually subtract the 2, and that's something we'll be generalizing later. But for right now, let's apply this to the problem we just saw, because we took a long time in that problem, to be honest. So let's see if we can do that justice, and hopefully it takes less time. Right, so this is the same exact example we saw at the very beginning of the video, where we want to find the volume of the solid obtained by rotating the region under this curve about the x-axis. So in between this and the x-axis, but about the y-axis, I should say, actually. So remember how the shape looks. We have this piece right here. We know that it goes from 0 to 1 because we found the zeros, which are the x-intercepts. This is the shaded region, which I'll shade in black. And then we're rotating that about the y-axis, so we know what the shape will look like, and that's fine. Now, remember that if you pick any particular x value in between, this represents the radius of our cylindrical shell, and the height of that particular x value, which is just f of x in this case, represents the height of that cylindrical shell. So by cylindrical shells, the volume must be the integral from 0 to 1, which are our x bounds, of 2 pi, so we can actually just pull 2 pi out like I showed previously. So that's fine. From where to where? From 0 to 1, so good, of x times f of x. So again, the 2 pi x part, because x is treated as the radius here, 2 pi x is the circumference of that shell, so it's that full length of that prism we saw, and f of x represents the height of that prism, and delta x represents that infinitesimally thin width of that prism. So this, I think, makes sense. And now all we need to do is, well, let's see, what's f of x? F of x is this function here, which is x minus x squared. So let's write that now. We have x minus x squared. And now to take the antiderivative, we'll have to distribute first. And we get x squared minus x cubed dx. So far this is looking not super similar to what we had from the previous way of doing it. But hopefully it becomes more apparent that it is actually the same value. I don't know, I'm still not super convinced yet. But let's see, antiderivative of x squared is 1/3 x cubed. Antiderivative of x cubed is 1/4 x to the 4th. And now we have to evaluate this between 0 and 1. Now luckily for us, when we plug in 0, they're both powers of x, so that's just going to be a big 0. Fantastic. And now when we plug in 1, what we end up getting is 2 pi times, when you plug in 1, you just get the coefficients 1/3 minus 1/4. And notice that if you kind of do this crisscross of subtracting fractions, you get 4 times 1 minus 3 times 1, which is actually, well, 4 minus 3, so that's 1. So it's 2 pi times 1 over, when doing that, we have to multiply the denominators, so we get 12. And look at that, after cross-canceling, we get the same exact answer we got before, because 2, of course, goes into 12 6 times, and we get pi over 6, which is the same answer we got before. Fantastic. Only look, it was way quicker, but it was utilizing this new technique of cylindrical shells. So we're obviously not done. I've only shown you one example, but at least I was able to show you the long way using 6.2 techniques, and then the fantastic way using this new method of cylindrical shells. So now let's take a look at a few more examples. All right, so for this problem, we'll be finding the volume of the solid obtained by generating the region bounded by the curves y equals x and y equals radical x about the y-axis. So this is a pretty similar problem, of course, but now we have these two curves instead of just one curve. So let's try to see what that's all about, of course, by graphing. I'm going to try to draw the graph kind of large so we can kind of look at some parts of this a little more closely. Now y equals x, of course, is this diagonal line like this. Y equals radical x looks something like that. So we know radical x is on top in the region that we're looking at, which is, of course, this region here, which I'll shade slightly. Okay. Now, of course, where they intersect, of course, is a 0 and 1. 0 and 1. And how I can tell is by plugging in 0 and 1, and they both satisfy that. But if you want to do it kind of more formally or algebraically, you can set the y's equal to each other as we've seen before. Square both sides. So we get x squared is equal to x, because when you square the radical, they cancel out. Move everything over, factor, and then set each of them equal to 0. We get x is either 0 or 1, so that checks out. And then you can plug them in to verify that this satisfies both of them actually. Great. All right, so that's fine, but now remember, we're rotating this about the y-axis. So when rotating this about the y-axis, the shape we get, so let's imagine flipping it across the y-axis first, and we get this kind of image like that. And then rotating around, we end up getting these kind of rings throughout. So we kind of see the shape we get, which looks kind of like this, this vase that's kind of not curved on the outside, but curved on the inside. So imagine that once the solid's been generated, it looks something like this, which is kind of like smooth on the inside like that, all around. So it does kind of like this funnel thing on the inside. In fact, that's kind of the best way to think of it as a funnel, but there's no actual hole here, it's closed in the bottom. But you could put things inside. So it's kind of like a vase type of shape. Anyways, how we're going to find this, of course, is by cylindrical shells. But notice for each shell, we actually have kind of like these two heights here. We have this height and this height. So in fact, it's a little kind of hard to show, but we end up getting this kind of weird region like this, which kind of looks a little funny. But again, when you kind of create a thin piece, this will be the piece we're rotating about for our cylindrical shell. And then, so maybe this is actually the best way of looking at it. And then this x value is traveling between 0 and 1, and we want to find the setup based on that. So now the radius of that shell, of course, is going to be x itself. The height will be this distance, which is actually straight up the difference between these top minus bottom. So it's going to be radical x minus x. So that part is pretty clear, I think. That the complete height is just the function on top, which is radical x. But then the lower height here is, of course, just y equals x. So the difference between radical x and x is, of course, radical x minus x, which is the height of the shaded region only. So now that we have the height, we have the radius, we're good to go. Because remember, delta x, or I guess dx, represents the width of that shell. So let me now erase this part to show the setup. And the setup, of course, is the volume equals 2 pi times the integral between our x values 0 and 1 of x, which is the radius, times the height, which is the difference between the functions. So it's radical x minus x, and then, of course, dx. Perfect. And now what? Well, now we want to distribute x. We'll write this radical, of course, as a 1/2 power to make the integration a little easier on us. Distribute. So we get the integral of x to the 3/2 minus x to the second dx. So let's write it like this, maybe. It looks a little better. In between 0 and 1 with 2 pi on the outside. And now antiderivative of x to the 3/2 is x to the 5/2 divided by 5/2, so multiplied by 2/5. Antiderivative of x to the 1/2 is x to the 3 divided by 3. We have that 2 pi on the outside, and we're going to evaluate this, of course, between 0 and 1. So let's do the evaluation first and then multiply afterwards. Notice again, like we've been seeing a lot already, when you plug in 0, we just get a big 0. When you plug in 1, we just get the coefficients, 2/5 minus 1/3. So we have 2 pi multiplied by 2/5 minus 1/3. And again, to do this in my head, instead of multiplying top and bottom of each of them by the opposite denominator, I'm just going to look at that crisscross pattern, which is 6 minus 5, which is 1, over 5 times 3, which is 15. So this is going to be 2 over 15 times pi. Or let's write it as 2 pi over 15. That sounds a little better. Great. So now let's take a look at one more example, and then we'll generalize what we've seen and kind of summarize things a bit. All right, so for this example, we want to find the volume of a solid generated by rotating the region bounded by this. So all of these problems are obviously kind of worded the same, so we're used to this phrasing by now, hopefully. But now notice this looks totally different because we have x in terms of y, not y in terms of x. And maybe it's a kind of subtle thing, but we're not rotating about the y-axis now. In fact, what we're rotating about isn't actually even a vertical line. Y equals -2 is a horizontal line. So this kind of reminds us more of a discs or washers problem from 6.2. But actually, if we kind of rotate things and tilt our head a bit, like I've been mentioning, well, this really actually is a cylindrical shell problem, or at least we can handle it as one. So we can use that method here. But something I should say is that, and what I'm about to show you isn't a very unpopular thing to do. We're not used to x in terms of y, so let's just swap x's and y's. So I'm going to swap all x's and y's. Everywhere I see an x, write a y instead, and vice versa. So applying this idea here, this swap, we get y is equal to 2x squared, y is equal to x squared plus 1, and then this is now about x equals -2. Now doing this kind of swap thing really just swaps the axes and you get the same shape. It's just kind of rewording things so it's in a kind of way we're used to, basically. If you wanted to graph it like this, you can. You'll get the exact same shape and solid I get, only it'll be vertical instead of horizontal. So let's see what that's all about. So I'm going to graph this, of course. So now, y equals 2x squared is a parabola that's stretched out by a factor of 2, so it's kind of a skinnier than usual parabola. X squared plus 1 is a wider parabola, but this is shifted up 1 unit. So it's a kind of usual parabola, but it's wider. So we actually get this region here, which I'll shade in black. But notice we're rotating this about x equals -2. Where do these intersect? Well, they better intersect before -2. So I'm assuming x equals -2 is going to be somewhere over here. We can actually find out where they intersect quite easily. I'm assuming they intersect at 1 and -1. In fact, you can plug in 1 and -1 into this and see if it works. And I can see that it does, because when you plug in 1 here, you get 1 squared plus 1, which is 2. Same thing here, you also get 2. So this is indeed 1 and -1. And then y equals -2 then would be this line over here. I'm sorry, x equals -2. Perfect. So we actually don't really care about the extended parts of these curves, we just care about this finite region here. And we're going to, of course, rotate this about this vertical line. And the shape we end up getting is a pretty strange looking one. It's this ring that has this kind of weird cross-sectional region, where it kind of has this, I guess you can call it like a railing around, something like that. So it has this kind of edge that's dipped in like this, all around. I said railing, I don't know if that's the correct phrasing that does that image that I'm seeing justice, but it's something like this. And it's very thin in the bottom. So the inside actually goes, like, connects to this. So if you were to have this object in your hands and look at the bottom, it would almost be sharp at the bottom here because it ends at a fine point. But it's smooth still, but it's not like you can put something in around, but at the bottom it's kind of thinner. Anyways, that's kind of the shape we get, but it doesn't really matter. We're going to find the volume of this using shells. But now, remember, for shells, we need a radius, we need a height, and that's it. So if we can find those things, then we're set and we're good to go. Then our volume will be equal to 2 pi times the integral between our bounds, which we'll find out shortly. In fact, the bounds are clearly -1 to 1, so that part I don't think is an issue at all. We have x, well, not quite x. X is what we usually expect to be the radius, but the radius is different here because instead of rotating about the y-axis like usual, we're rotating about this shifted vertical line. So our radius is actually different. In fact, if we pick any x value in between -1 and 1, let's see if we can kind of get the idea of what's going on here. Pick any x value between -1 and 1. What is the distance from this? I guess it's going to be, I want to say that it's going to be 1 plus, because this distance here, from x equals -2 to x equals -1 is, of course, well, 1. The distance is 1. And I want to say that this distance is x, but that's not quite the case. And in fact, it's kind of hard to show because here x is going to be negative. So if you do add 1 to x when x is negative, I don't know if that'll quite do it justice. Let's imagine x is positive and let's get an idea, and then we'll figure out what happens when x is negative. So when x is positive, I think this actually makes a lot of sense. This distance is going to be 2. This distance will be x going from 0 to actually where x is. That makes sense? Good. But now notice when x is negative over here, then this distance is actually still going to be 2 plus x. Because when x is negative, we'll have 2 minus that x value actually. So you can kind of see it when x is 1, for instance, 2 plus 1 is 3, and that's this total distance here. When x is negative 1, 2 plus negative 1 is 1, which is this distance here. So that, I think, is the way of describing the radius as x goes from negative 1 to 1. The radius is just 2 plus x. So let me write y is equal to 2 plus x instead of our usual x. So more about that in a bit when we finish this problem, and we'll kind of generalize and summarize, similar to how we did in 6.2 actually. So our radius is 2 plus x actually. Our height is still what we saw last time. It is, notice, the difference of these functions. The total height is to the upper function, which in this case is this guy. The lower height is to this function, which is 2x squared. And the difference between them is actually the total height of this piece here that we're rotating about the line x equals negative 2 at that particular x value. So notice as x floats from negative 1 to 1, this distance actually changes. It's really, really thin here, then it gets thicker and thicker, and then here it's kind of really tall, and then it goes back to being really small. So you can kind of follow these lines here. Small, large, large, larger, and then back to small. But anyways, it's clearly going to be the top minus the bottom, which is x squared minus 1, or I guess plus 1, minus 2x squared. Fantastic. And by the way, I think I mentioned earlier without doing it, the way I found these bounds was just by guessing and plugging in. But if you actually set them equal to each other, you get negative 1 and 1 anyways. But I've kind of shown that already, so if you want, you can try it on your own and you'll get that result, hopefully. And again, the height now is going to be the difference of the functions, which we found out that x squared plus 1 is the one on top, minus 2x squared dx. So now if we combine these, we get negative x squared, so it's 1 minus x squared actually. And then if we distribute this, so FOIL out basically, we get, let's see, 2 times 1, which is 2. 2 times negative x squared, which is negative 2x squared. Then we get positive x, and then negative x cubed. All of this inside the integral from negative 1 to 1, 2 pi on the outside. And I really should have wrote that all of these decorations here as well, but let's just imagine this is just us simplifying the integrand and then finally here. Now nothing actually combines here, which is okay because it's not too many steps. I wish I could say that this is an even or odd function because we have negative number to a positive number, so we have kind of opposite limits. But unfortunately, all these powers are not all even or all odd, so we can't actually pull that trick off, unfortunately. So instead we'll have to take the antiderivative like usual, which is going to be, let's see, antiderivative of 2 for this guy is 2x, then it's a negative 2 over 3 x cubed, positive 1/2 x squared for this guy here, and then minus 1/4 x cubed. Evaluated between negative 1 and 1. It's going to be a little bit of a doozy, but let's see if we can do it. In fact, just to show more work, I'm going to create some space above here and then continue this. Okay, so here I've erased things, shifted up our last result, and now let's continue. So when you plug in 1 into this mess, we just get the coefficients, which is 2 minus 2/3 plus 1/2 minus 1/4, and that's it. That's for the first evaluation minus. When you plug in negative 1, you kind of get the same thing, only all of the even powers remain positive and all of the odd powers change sign. Because of course negative 1 to an even power is positive 1, but a negative 1 to an odd power is a negative 1. In fact, you know what, I kind of made a mistake here. This should have been 4. I may have miswrote that in the previous step, but it should have been 1/4 x to the 4th. Anyways, when you plug in negative 1 to the odd ones, you get a sign change. When you plug it into the even powers, you get no sign change. So there's going to be negative 2 plus 2/3, because that's sign change. Negative 1 squared and negative 1 to the 4th are positive 1, so we get the same sign, plus 1/2 minus 1/4 for those. Awesome. So sign change for the odd powers, no sign change for the even powers. Distributing the negative here, and then close parentheses for this whole thing. So we get 2 pi times, let's see, it's 2 minus 2/3 plus 1/2 minus 1/4 plus 2 minus 2/3 minus 1/2 plus 1/4. Awesome. So some things actually do cancel out completely. The 1/4 and 1/2 do, the last two terms. Basically the even ones actually do. Perfect. But now what we have left on the inside is just these two combined. So that's 4, and then these two combined to negative 4/3. So we get 4 minus 4/3. In fact, if you want, and this is maybe being a little too detailed and kind of a little showy-offy, if you will, but if we pull out 4 from this and multiply it to 2 pi, we get 8 pi times 1 minus 1/3, which I think is just easier to do in your head a little bit. 1 minus 1/3, of course, is 3/3 minus 1/3, which is 2/3. So this is really 8 pi times 2/3, which is now 16 over pi times 3. Well, 16 over 3 times pi. So 16 pi over 3 is what I meant to say, really. Whew, nice. So it's a little wild, but the setup wasn't too bad, actually. So with cylindrical shells, and even with the discs and washers, the setup isn't actually bad at all. But now what I want to do is I want to generalize kind of like I did in 6.2, where I gave you this kind of equation for the x way and y way of looking at things, depending on what we're asked to find, actually. And notice it was just a swap in variables, kind of like we saw here, actually. And also notice that if we were to leave this as is without making this swap, the image we get is exactly this, but rotated. So in fact, it'd be kind of flipped, where this line would now be down here at y equals -2, and we'd have to imagine this on the side rotating around like that. But it's best to view it like this so that we can see it as a shells problem. Okay, so now let's go to the generalization and see what it's all about. Right, so if you had seen what I shown in 6.2, this is essentially the same statement, only the formulas look a little different, because of course the formulas from that section was to do with disc and washer methods, but here it's with, of course, cylindrical shells. So this formula here is basically the general cylindrical shell formula, and similarly with this formula. But of course we have a kind of X version and a Y version, depending what we're rotating about. So if you're rotating about a vertical line and you have two functions between two X values, so kind of imagine we have something like this, where we have a top function f of x and a lower function g of x, f and g, in between these two x values a and b on the x-axis, and rotating this about a vertical line, usually the y-axis, in which case, notice the y-axis is of course the line x equals 0, so in this case it'll just be x, and then we just get these usual things, just f of x minus g of x. Now the reason why it's absolute value for both of them, this one I'll talk about in a moment, but this one of course is just so we don't have to know which one's on top and which one's on the bottom, because taking the absolute value will ensure we always get a positive difference, even if they have these kind of intersections in between, like we mentioned in the previous section. Now, why we need absolute values here is basically because in this scenario, if the way it's looking like, so imagine of course this is the y-axis, but instead this is the line y equals x naught, or x equals x naught, just to be kind of general, then the distance here the distance actually kind of depends. Basically, it's the distance between x naught and the y-axis, so it depends where the y-axis is located. So, but in general, this is going to be, so again, imagine like the y-axis is way over here, for instance. That's the y-axis. This distance is going to be a minus x naught. So if you pick any x value in between, then you get x minus x naught for this distance for the radius. So that I think makes sense. So that's why I have x minus x naught. Why it's in absolute values is if we actually have the scenario where this is on the other side of things, then x minus x naught will actually be a negative. But since we want a positive radius, we take the absolute value to ensure that's the case. So believe it or not, this is actually a general formula that you can use for any of the previous problems that we've seen in this video. And again, for rotation about a horizontal line, y equals y naught, we need everything instead of in terms of x, insert in terms of y instead. And our x and x values, a and b, our limits, must be y values now. And really what we end up getting really is just the same image here, only with a swap of the x and y axes. In fact, everything has a swap. All of the x's are replaced with y's and vice versa. Kind of like we saw in the last problem, we actually just did that translation straight up from the get-go to make things a little more kind of simple for us. Otherwise, you have to tilt your head and think about it. It's not bad, it's good practice to try in doing that, but I always recommend to try doing it the way I suggest here, and then comparing to kind of train your way to that point, so to speak, if you want to get to that point. But it's entirely up to you. Knowing that you can actually transition just by swapping x's and y's is a very, very useful idea, and it's so simple too. Some people just kind of forget you can do it. But anyways, I've explained that. Awesome. So that's it. That's everything we need to know for cylindrical shells. We've only done, I think, like maybe three or four problems in this section. But they were good problems. It, I think, generalizes everything. You kind of are set to go. Hopefully you can try problems on your own and be good based on the information I've given you here in this video. Really hope you enjoyed this. Thanks for watching. I'll see you guys in the next video where we'll be discussing 6.4 and 6.5. It's going to be a lot of fun like always. See you then.